Hey everyone, today we are going to focus on a second day of Power Series. It shouldn't take as long as the first video. So the first thing we want to talk about is just have a couple extra thoughts that I'd like us to share, or I'd like to share with you, I guess. When you're working with Power Series, a couple things you want to think about. Really with Power Series, the ratio test is a pretty good test to use. Works great if you're trying to find the interval of convergence. So if that's what you're being asked to do, the ratio test is a pretty good choice. Don't forget to check the endpoints by substituting in values, those values that are the endpoints. And then just as an extra thought, understand that the interval of convergence, so the IOC is what I'm going to call it here, can be an open interval, can be a closed interval. It can be all reals, so infinity, negative infinity to infinity, or it can be only 1 point even, okay? Point, because I should just write instead of type. Okay, so we're gonna do a few practice problems to get you ready for the assignment you're gonna get in class tomorrow. So here's the first one. So you wanna find the interval of convergence for this series here. So like I said a few minutes ago, it tends to be helpful to do this, get the pen here, with the ratio test. So that's what we're going to do. So ratio test, I'm going to do the limit as n approaches infinity of the absolute value, and the absolute value is definitely more important here than it was before. And when I do the absolute value, the negative ones at the end can be dropped. And this becomes x to the 2n plus 1, fix that, divided by 2 times n plus 1. And then I'm supposed to divide by the original, and I'm just going to flip it so that it becomes 2n over x to the 2n. Okay, continuing with my limit. There's some of you out there that need to get better with showing good mathematical steps, so please make sure you're writing out all of your limits here. Or all of the words limits, but you know what I mean, everything. I'll make sure you're being careful with what you write. All right, so this is actually x to the 2n plus 2, so I get x to the 2n times x squared times 2n all over 2n plus 2 times x to the 2n. I'm going to reduce, and I am left with 2n over 2n plus 1 goes to infinity, right? Goes to 2, so that limit, I'm really struggling here. It goes to 2 over 2, which that limit is 1, but then I have to take into account the x squared, so I'm really left with the absolute value of x squared, which then I'm going to use that to find my initial interval of convergence. So the x squared should fall between -1 and 1. Square root both sides, I can't deal with that, but the square root of 1 is -1, so I still get this as my initial interval. And then I have to check the endpoints. And I check the endpoints by substituting -1, because that's my left end, and then +1 in again. So I'm going to substitute -1 into the original problem. So I don't need that limit there, sorry. So the sum from 1 to infinity. Oh, I'm looking at my handout, and my handout says 0 on it. I'm sorry if yours still says 0. Fix it to be a 1 if you did not. Just catching it on the handout I'm looking at for the problems here. So this should be a 1, otherwise it won't work. So make sure you change that to a 1. Okay, so when I substitute -1 into this original problem, I have -1 to the n times, if I put -1 in for x, but I'm raising it to the 2n power, is really squaring it, so I'm still just getting a +1 over 2n. Okay, so now we want to think about all of the convergence tests that we've already done. So we know, I'm not even going to worry about showing too much work because I think you guys can answer these questions now. We know that 1 over 2n, whether it's a 2, a 3, or 100 down here, 1 over n diverges. So this has a diverging going on, but then when I throw the negative out front of this is behaving like the alternating harmonic series, so this thing actually converges by the alternating series test. Okay. Now I'm going to check x equals +1. Well, just knowing what you know about this problem, hopefully you'll understand that this should behave in the exact same way because it's just putting a 1 in there. So same thing, this converges also for the same reason, behaving like the alternating harmonic series. Since these both converge at both endpoints, we say that the interval of convergence is from -1 to 1, and you have brackets. Okay, so the endpoints are included here. All right, we're going to try another one. So now we have -1 to the n, x to the n plus 1 over n plus 1 factorial. So we're going to deal with a factorial here. So again, I'm going to do the ratio test. So my ratio test is going to give me, again, when I do the absolute value, the -1 to the n is not necessary anymore. And this becomes x to the n plus 2 over n plus 2 factorial, and then times the reciprocal of this. So n plus 1 factorial over x to the n plus 1. Okay, and I'm going to do a little simplifying of my powers. And if you're faster at this, if you've got other ways that work, feel free. If you remember some things from Honors Pre-Calc that you know you get faster, you do not need to show all of these steps. X to the n times x squared times n plus 1 factorial over n plus 2 times n plus 1 factorial times x to the n times x. Okay, so the factorial, n plus 1 factorials go away, the x to the n's go away. There's an x, that's an x squared. Sorry, that handwriting is bad. And I'm going to cancel those, so that's gone, and I'm left with x in the numerator and n plus 2 in the denominator. So as this goes to infinity, the whole entire thing goes to 0. Okay, so since this limit goes to 0, it means the thing converges everywhere. It doesn't matter what values for x we put in there. We don't have an interval of convergence, so we would actually say the interval of convergence is all reals or from -infinity to infinity. Okay, so now we're going to talk about some things that we maybe remember a little bit from last year, actually. So we want to figure out the interval of convergence on this, but we have to first write a series for this. So this is something that we learned last year. This is actually the formula, kind of, a version of the formula for the sum of a geometric series. So we want to rewrite this so it looks like 1 minus the ratio. There's always more than one way to do this. I'm going to show you the way I was thinking of, and then if you have another way, feel free. So I'm going to rewrite this as 1 minus, and I'm just going to figure out what needs to go in parentheses here so the whole thing becomes 7 minus 2x. I'm going to make it be a positive 2x, and then if I make this a -6, the whole thing will become a positive 7. So I'm going to use this to create my series. So the series, we usually just do 3 terms, 3 or 4 terms. So the first term is the top number, 3. And then since it's minus here, everything is actually plus over here. It's kind of the opposite. So it's going to be 3 times 2x minus 6 plus 3 times 2x minus 6 squared, dot, dot, dot. Okay. The interval of convergence will be 2x minus 6 is between 1 and -1. So I'm going to add 6 and divide by 2. So this is my interval of convergence. I'm so sorry. And this is my series. Okay, moving on. Number 4. Same idea, but now I've got a center at 0. So this actually can be a little bit easier to work with. I have to divide instead of rewrite the whole problem. So when I divide, I'm going to divide by 4. So if I divide by 4, I get 6 over 4 over 1 plus x squared over 4. This is almost exactly what I want, but remember I want first term over 1 minus the ratio, so I have to have a minus sign here. I'm going to reduce the numerator. I'm going to rewrite this as 1 minus negative x squared over 4. Okay, so when I write the series for this now, the first term is 3/2, and I multiply 3/2 by negative x squared over 4. So it'll be minus 3x squared over 8. Then I multiply this by negative x squared over 4. So it becomes positive 3x to the 4th over 32, dot, 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 and so forth. Okay, the interval of convergence is going to be negative x squared over 4 between 1 and negative 1. So this is going to be negative 4 is less than x squared is less than positive 4, which really means I'm taking the square root of just this number. So this is between negative 2 and 2. And you can see the center is 0, which is what you were asked for. Okay, moving on to the next problem here. So first of all, I probably whited this out in about half of yours. The wrong series was typed here, so you want to fill in what is written here. So this is the series for tangent, inverse tangent, and you'll be focusing on these a lot more in the next section. But for now, I just wanted you to see what it is. So this is it in sigma notation, and then this is the actual series written out. And we want to use this series for inverse tangent to find a power series that would represent 1 over 1 plus x squared. So when you see something like this, you want to be thinking about what do you know about this function that you could do to it to create this function. So hopefully as you're looking at these things, you're recognizing that inverse tangent, oopsie, has a derivative of 1 over 1 plus x squared. So I could take the derivative of this and get 1 over 1 plus x squared. So I'm going to actually write that here. So the derivative of tangent x, inverse tangent, is 1 over 1 plus x squared, which means if I take the derivative of its series, which the series for inverse tangent is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so forth. If I take the derivative of all of these terms, the derivative of these terms will be the series for 1 over 1 plus x squared. So this derivative becomes 1 minus, take the derivative of this, x squared. Derivative of the next term is positive x to the 4th. Derivative of the next is negative x to the 6th, and so forth. And hopefully you're starting to think about how to write this as like the nth term. So the nth term of this would be negative 1 to the n, and then you're taking x to the 2n. Okay. So when you look at that, hopefully you see that, you put 0 in, you're going to get 1. You put 1 in, you're going to get negative x squared, and so forth. All right, so we're going to actually look at the same, we're going to try to do the same thing, so create the same series. Oh, I got a whole bunch of stuff here accidentally. We're going to create the same series here, pretend like you saw nothing. But we're going to create it from the function 1 over 1 minus x. So again, next section, you're going to really be focusing on kind of memorizing or knowing this series, but for now I'm telling you what it is. So the series of 1 over 1 minus x is this thing here, and I want to use this series to create a power series for this same function. So instead of dealing with inverse tangent's derivative, I am going to rewrite 1 over 1 plus x squared as 1 over 1 minus negative x squared. And so notice how similar that is to this thing up here. So what I'm going to do is I'm going to substitute negative x squared into this series wherever I see an x. So this will become, the first term is going to stay 1, and then the x becomes negative x squared. And then the x squared, well, I'm going to substitute x squared in squared. And then I'm going to substitute negative x squared cubed in, and so forth. And so this becomes 1 minus x squared plus x to the 4th minus x to the 6th, which is exactly what we had on the last slide, because it should be the same thing no matter how you do it. I hope you're getting the hang of it. You're going to see some problems like this on the worksheet that you're going to get tomorrow in class. So do your best, and we'll see you then.